The last intermolecular force we're looking at is called ion dipole. It is the strongest out of all the intermolecular forces we've looked at. An ion dipole occurs with exactly what it says in the name, an ion and a molecule that has dipole-dipole. So you have to have two of those. So it looks a little bit different. We're not just looking at one molecule, we're looking at two. So something that has ions and a molecule that is dipole, so polar molecule. So you can see here we have sodium and chlorine and water. So if I were to put sodium chloride into water, the water will start to pick apart the sodium chloride. So the partial negative side of water will surround the positive sodium and pick that off. And then the partial positive side of water will surround negative chlorine and start to pick those off. So that's why when I put a soluble ionic compound into the water, it will dissociate because the water surrounds each of the ions and pulls them apart. So that's the whole reason for that dissociation occurring. Okay, so here's just a summary of what we talked about. Ion dipoles are the strongest, and it gives that example there, sodium and water. So again, you have to have the ion and you have to have the polar solvent. So you'll have two things there. And then hydrogen bonding is the next strongest. So hydrogen covalently bonded to oxygen, nitrogen, or fluorine. And then dipole-dipole occurs in polar molecules. So again, make sure you go over how do you know whether a molecule is polar or nonpolar? We didn't really talk about dipole, induced dipole, so I'm not going to ask you any questions about that. And then the last one, London dispersion forces, can be induced dipole, or we looked at instantaneous and induced dipole, and it has to do with polarizability. And this is these are in everything. So everything has London dispersion forces. This is a nice little flow chart to kind of help you decide what type of intermolecular forces you have. So if that's helpful to use. And remember, London dispersion forces are the weakest, and then ion dipole forces are the strongest in our intermolecular forces, but then ionic bonding and covalent bonding are the strongest out of all of them, because intramolecular forces are much stronger than intermolecular forces. Okay, just have some examples here of how we can combine what we learned with the properties in the beginning of the chapter with the intermolecular forces. So in this one, it says list the substances in order of increasing boiling point. So we're not going to go look up the boiling point. We're going to put them in order based on the strength of their intermolecular forces. So we have BaCl2, H2, Ne, CO, and HF. Okay, so BaCl2 is kind of tricky. It's ionic, so it's going to have, intramolecular forces. So this one's going to be the strongest. So that one was a little tricky. So this one's the strongest. Okay. So next we're going to look at what type of intermolecular forces these others have. We're going to look at the size of them. So we'll start with that. Let's figure out what's their molar mass. So hydrogen molar mass is 1, and we have 2 of them, so it's 2 grams per mole. Neon is going to be 10. So that's just the weight on the periodic table. CO, carbon monoxide, is going to be 26. So 1 carbon, 1 oxygen equals 26, and then HF is going to be 20. Oops. So that gives us an idea of the size of the molecules. Now let's go through and figure out what type of intermolecular forces they have. So H2, it's nonpolar, so it's just going to be London, right? London dispersion forces. That's all it has. Neon is kind of like our helium example. So it's going to be just London. It's a nonpolar. But then CO, okay, oxygen is very electronegative. We have carbon. so that we're going to have a polar molecule there. So we're going to have dipole, and we're going to have London dispersion, because London's in everything. And then last one, HF, we have hydrogen covalently bonded to fluorine. So we're going to get hydrogen bonding. It's polar, so we're going to get dipole, and we're going to get London dispersion. So all three, okay? But the strongest one, the strongest intermolecular force, is the one that determines the boiling point. So those are the ones we're focused on. I left out an N. Okay. So we know that barium chloride is the strongest. So the next strongest is going to be hydrogen bonding. It's going to be HF. Okay. And then dipole we know will be the next strongest. And then we're looking at the two with the London dispersion. So we have neon and hydrogen. Well, since neon is bigger, it's going to have stronger intermolecular forces, which is going to make hydrogen the weakest and with the lowest boiling point. Okay, we'll do the next example. This one says, is the surface tension greater in CHBr3 or CHCl3? Okay, so CHBr3, is going to look like this. So they're both going to look very similar. But the difference is chlorine is smaller than bromine. So bromine's going to be bigger, which means this molecule here is going to have stronger intermolecular forces because it's bigger. So the question was, is the surface tension greater in CHBr3 or CHCl3? And what we know about surface tension is, as the intermolecular forces get stronger, the surface tension is greater. So the surface tension is greatest in our biggest molecule. Okay, and then the next one said, would you expect the viscosity in pentane? So pentane has 5 carbon. This is pentane. To be larger or smaller than the viscosity in hexane. Hexane has 6 carbon. So both of these just have carbon and hydrogen. So they're nonpolar molecules. So they only have London dispersion forces. So we know pentane, since it has less carbon and less hydrogen, is going to be smaller, which means it's going to have weaker intermolecular forces. So let's put that here, weaker and stronger. Okay, so the bigger one's going to have stronger intermolecular forces. So now, would you expect the viscosity of pentane to be larger or smaller than the viscosity of hexane? So remember, viscosity increases with the strength of intermolecular forces. So the viscosity of pentane is going to be smaller than the viscosity of hexane, because pentane is smaller, it'll have weaker intermolecular forces, and it will be able to flow easier.